Proof of concept number 3 in Evolve project deals with the task of driver distraction detection. We at Virtual Vehicle want to contribute to a system that detects driver detection independently of the used car and could be therefore easily used by everyone. The situation could be like this. Imagine that you are sitting in your car. Your smartphone is placed in front of you and records your driving. A video stream is created. This video stream will be sent to a trained model on your smartphone. An app uses this model to detect if you're distracted or if you're focusing on the driving task. To get to such a model, it has to be trained, and this training will be done with the help of the Evolve platform. Firstly, we will take the training dataset and store the data on the Evolve storage. After that, we will pre-process the data and use the final data to train and store the machine learning model on the platform. Speaking about the data, the dataset used for training consists of 10 classes, from talking to passengers to safe driving, and it is stored on the Evolve platform. To store and process the data on the platform, we need different services. A quick overview will show the main used services. Prior to the service overview, we will have a quick look at our data. Therefore, we go to the login page and enter our credentials and click login. So a few moments later, we are on the Evolve dashboard, and there we have different tabs: services, templates, images, datasets. To get to the data, we have to click Files, and there we have our folders. And I already uploaded the data, so I go to the image folder, and there we go, we have the train folder, and there are the images already structured in different folder types. For example, C0 stands for safe driving, C1 for talking to passengers, and so on and so forth. That's how data is stored on the Evolve platform. Let's have a quick look at the services we are using on the Evolve platform. To create a new service, we simply click on this button, New Service, and there we go. We have our first service we are using. It's the Zeppelin TF GPU service. It's a notebook server with TensorFlow and GPU support. Another service we are using, especially for distributed training, is the MPI TF GPU service. It's a cluster of pods supporting MPI running on GPU. To use this service, we need another service, namely the QBlock service. It's a service where we use the terminal and the web console to use the MPI service. Another very useful service is the TensorPort service. It's the visualization toolkit for TensorFlow. To create a service, we click the Create button, but for now, I will click the Close button because we already have our needed services in our service list. Let's have a look how the Zeppelin notebook server can be used to train a model that is able to detect driver distraction. So first of all, I make a quick check if we are using the GPU in this notebook. So here, quick check, we are using the GPU. Then we have to import all the necessary libraries in Python to make sure we can use them further down. Next, we have some configuration lines. So where's the data? How many classes do we have? And so on. And then we continue with loading the images. So we have training image data, we have validation image data, and of course we have the test image data. The next thing is the creation of the model. So here we have our model, our CNN model we use for training. So here we can have a quick look at it. It's quite an intense model. And the next step is already the training. So we start with fitting the model. So here we can see I already started it, that we can have a quick look. So I trained it for 100 POCs. So here we see, and the loss and the accuracy is getting better and better over time. The next step is to save the model. And of course, would be interesting to see over time how the model is doing. So in blue, we have the training accuracy, and in orange, we have the validation accuracy. As you can see, they're quickly rising here, and they even touched the 100%. And here we have the loss. It should be the opposite, and that's the case. And here we see. So here we count our test loss, and we have a test loss of 0.05 and the test accuracy of 0.98. So, but now we want to show it in a confusion matrix because it's really nice to have a look at it, and we see this kind of confusion matrix when using the model to predict driver distraction on the test data set. So here we have the true values and the predicted values, and safe driving is 98.80% of the time correctly predicted, and so on and so forth. We have some not so good predictable classes here, for example, hair and makeup. So sometimes hair and makeup is also recognized as reaching behind, or here talking to passenger, but overall it's really good. So we can have a look at it on the image data. So we predict the test data, and if you see the data class or the distraction class in green, it's a correctly classification of the image. So here all the images were predicted correctly. So the test data we have, but it would be interesting to predict on really unknown data. And here we don't have a label, so we have to check on ourselves if it's true or not. So for example, we can obviously see the woman is adjusting the radio music player. This one is talking right, reaching behind. It looks really good. So that's just a quick introduction how we can use the Zeppelin notebook server to train a model to predict driver distraction. Let's continue with the distributed training with MPI and Harvard. Therefore, we choose the CubeBox servers, CubeBox here, and we see the console. Here we have to enter our namespace, and we have our MPI pods. You can enter one with clicking R, and here we are. Let's list all the files in this pod, and especially the host file is interesting as we are defining our GPU number, or our number of GPUs we are using. So we're using in total 6 GPUs. To start this, we have to run Harvard run, and P for 6, so we're using 6 GPUs. We define host file. As already said, we are using the Harvard host file, and we have to define the file we want to execute. So it's our file with our TensorFlow model. We have to type in the path and of the file and the file itself. Click enter, and the distributed training is starting. In the end, we have a look at the performance of the distributed training with MPI and Harvard. To get a feeling, we compare the times on a client machine, a really good one, and with the Evolve distributed training. So we here see the client needs about 660 seconds, whereas the Evolve distributed training needs only 43 seconds. That's 15 times faster. And also the prediction is, of course, faster, not as much as the training, but 7.3 times faster. So in general, we see we have a really good model prediction with an accuracy of 98%, but of course there has to be some further research when we use other data than the used training data. But overall, we can say the evolved distributed training is really worth looking further into it, and we're happy to be part in the Wolf project.